Okay, welcome back. So, we went through, I think it was section 4.2, and there we saw linear second-order differential equations with constant coefficients, and they were also homogeneous equations. So there, what we saw is what happens when we have real roots. This time, we're going to be talking about what happens when you have complex roots. Now, complex roots, they're always going to happen in what are called conjugate pairs, and that's because we have real coefficients. And what we're going to end up finding is that each of these can actually go back into the same guess that we made before. So we're actually going to be making the same guess. We're going to be making y is equal to e to the rt as our guess. Throwing it in there, and you're going to be able to factor out e to the rt just like before. And you're going to have, say, ar squared plus br plus c is equal to 0, just like before. But what's changing is that we're allowing the possibility that we're actually going to have complex roots. So let's say we had the differential equation, being second derivative of y plus y is equal to 0. When you take a look at that polynomial, you're going to end up getting r squared plus 1 is equal to 0 as a characteristic equation that comes out of it. And what ends up happening there is that you're going to have plus and minus I as being your real roots. Now, you can plug those back into e to the rt to get e to the it and e to the minus it. And those are each solutions to the differential equation. They're complex valued, so maybe they don't represent the system that we really care about, but they are actual solutions. So we'd really like to not deal with complex solutions, and so I'm going to show you something in this class where basically you can take these combinations of these things, and what you're going to end up having is that you can just consider the real and imaginary part of the solution. In this case, what that's going to be is e to the it can be written as cosine plus I sine of t. And it turns out that cosine and sine are both independently solutions to the differential equation, and we can just go ahead and take those as the solution, and rather than considering the i's, e to the its. So, but first, it helps to have an idea of what's going on, so we're also going to talk about Euler's equation. Euler's equation is basically what I just told you, where basically if you take e to the it, you get cosine plus I sine. There's a couple ways to prove it, and it's kind of fun, so I thought I'd go ahead and show you. And yeah, so that's basically going to be the whole section, and that will be us wrapping up for what we call second order differential equations with constant coefficients and also being homogeneous. So then the next step, I believe, is going to be the method of undetermined coefficients, where we allow for the right-hand side to not be simply 0, but it could be a function of t. And there's a whole bunch of rules for how we would make a guess or adjust our guesses in order to come up with what we call a particular solution. But that's not going to be today. Today we're just talking about, or even this week, honestly. So today we're just talking about the homogeneous case, and we'll get to the other case later. All right. Thanks for listening, and now let's go ahead and jump into the lecture. Okay, so let's go ahead and get started. There's some writing here because I started writing and didn't realize I wasn't recording, so I erased about half the lecture and starting over here from almost scratch. So again, here we're talking about section 4.3, and this is out of Nagelstaff and Snyder's Fundamentals of Differential Equations. So the title of this section is Auxiliary Equations with Complex Roots. And so the idea is that we're extending what we did in section 4.2, where we had distinct and real and repeated roots, but they're all real. And so we knew that we can get two solutions to the differential equation ay double prime plus by prime plus cy is equal to 0. And this led to an auxiliary equation where we have ar squared plus br plus c is equal to 0. Now, we're looking for the roots of this auxiliary equation, and if we find the roots, then we can make, if they're distinct, for instance, we can make two linearly independent solutions with this exponential, where we take r1 and r2 as being the roots for the auxiliary equation.
And if it's a repeated root, so say r minus r naught squared, then we get y sub 1 of t would be e to the r naught t, and y sub 2t would be t e to the r naught t. Now the question is, what do we do if it's complex? And so the answer would be, so say you get alpha plus or minus I beta. And so the answer to that would be, you have y1 of t is equal to e to the alpha plus I beta t. This is the root to the equation after all, so it should have to go in there. And this would be written as e to the alpha t times e to the I beta t. And you have a second solution, y2 of t is equal to, say, e to the alpha t times e to the minus I beta t. Now, so this is one route you can go. These are basically two linearly independent solutions, and they are solutions to the homogeneous equation. However, it's going to turn out that we don't actually have to appeal to these complex numbers, but let's take a few steps and see why that's true. Okay, so if we have alpha plus I beta, alpha and beta are both real numbers, and we're looking at this equation, e to the alpha plus I beta t. I just said a second ago that this can be written as e to the alpha t times e to the I beta t. Now, this piece is nice and easy. Alpha is real, t is real, and we can certainly conceive of how you could compute that. But then the question is, what do you do about this? I is complex, is an imaginary number, and so what is e to imaginary number? And so this is what we're going to appeal to Euler's equation for, or Euler's formula. And there, Euler tells us that e to the I theta is equal to cosine of theta plus I sine of theta. Now there's about a half dozen ways of proving this, but what we're going to do is we're going to appeal to the power series. So e to the I theta, just putting in I theta into the power series expansion for e, or e to the x, we get this. We get n equals 0 to infinity of I theta to the n over n factorial. Right, and expanding this out, so we get 1 plus I theta over 1 plus I theta, and that's squared, divided by 2 factorial. Let's put a factorial on the 1 too. Plus I theta cubed over 3 factorial, and I theta to the fourth over 4 factorial, and etc. Now I wrote out 4 terms because it's going to help us see a pattern coming out of here. What we need to figure out is what to do about all these i's. We want to simplify it, and ideally we'd like to simplify it into cosine plus I sine. So let's take a look. Well, I to the first power is just I. I squared is negative 1. And I cubed is I squared times I, so that's going to give us negative I. And then I to the fourth is, well, I squared squared, and so negative 1 squared is just 1. But if we put I0 as being 1, we start to see a pattern coming out here. This is just going to end up looping over and over and over again. So I can go ahead and expand it out. Like I can change things like this. So I'm going to have 1 plus theta I over 1 factorial. And then I have negative theta squared over 2 factorial. Now we're going to have negative I times theta 3 over 3 factorial. Now we're going to have plus theta to the 4 over 4 factorial, etc. So now let me group everything that has an I and everything that doesn't. And so for everything that does not have an I, it's going to be 1 minus theta squared over 2 factorial plus theta to the 4 over 4 factorial, and then presumably a minus next. And then plus everything that has an I, so I'm going to factor I out. I get theta over 1 factorial. I get minus theta cubed over 3 factorial. And I get plus, etc. So rewriting this, we get sum of n equals 0 to infinity. This first term is going to be -1 to the n as an alternating series to theta, and now it looks like it's only even powers. It's going to be 2 theta to the 2n over 2n factorial plus I times the sum of n equals 0 to infinity of theta divided by, say, 2n plus 1 factorial to 2n plus 1. So we only get odd numbers out of this. And again, it's an alternating series, so -1 to the n. All right, the astute student will notice that this is just cosine of theta plus I sine of theta, and that's the formula. Okay, so this is called Euler's formula. You could actually prove it using differential equations, but we'll leave that alone for now. So this is pretty standard, this approach, actually. So what that means is that if we go back up here, I can write this as e to the alpha t times sine of beta t, or say, let me just, e to the alpha t is cosine of beta t plus I sine of beta t. Okay. Now, what's important about that? So remember, we also have these come in conjugate pairs. And so we end up having a minus sign come out of here, and that would just come from putting minus beta into sine, and then using the odd property, and then cosine wouldn't be changed because it's an even function. So that gives us two different solutions to this sort of differential equation. And so now if we say that if y1 of t is equal to e to the alpha t times cosine of beta t plus I sine of beta t. And the other solution is y2 of t is equal to e to the alpha t times cosine of beta t plus I sine of beta t. Now I can tell you something that is maybe previewing of what's going to happen in the superposition principle, but any linear combination of these guys, and we said the general solution then is c1 times y1 plus c2 times y2 is a solution to the homogeneous equation. And that is assuming that this solves ay double prime plus by prime plus cy is equal to 0. And so if it does solve that, then their linear combination also solves it. Now, why is this helpful to us? Well, I can get rid of the complex numbers right away. And so I'm actually going to show you a way of getting a different kind of solution, and this is ultimately what the chapter is leading into. But if I take, say, y1 and I add it to, oh, and that should have been, oh, that's way too big. That should have been my sign there, my mistake, sorry. So if I add these two equations together, so y1 plus y2, what do we end up getting? Let me switch to another color. I don't like it. What do we end up getting? Well, so we're going to have e to the alpha t times cosine of beta t plus I sine of beta t plus e to the alpha t times cosine of beta t minus I sine of beta t. If I add these two guys together, this ends up giving me 2 times e to the alpha t cosine of beta t. Now I can also choose to have c1 and c2 being complex, or I can just worry about just taking the difference and then I'll divide out by a complex number later. So I take the difference of these two guys and I get e to the alpha t times cosine of beta t plus I sine of beta t minus e to the alpha t, then we have cosine of beta t minus I sine beta t. right? So now this term ends up subtracting off from this term, and that ends up canceling. So it's just going to give me, say, 2 times I of e to the alpha t sine of beta t. Okay, and so then that tells me that y1 plus y2 divided by 2 is equal to e to the alpha t cosine of beta t. And then I have y1 minus y2 divided by 2i is equal to e to the alpha t sine of beta t. So remember last time what we said is that if say I'm going to say YA and YB are linearly independent solutions to, say, star, then every solution may be expressed as say y of t is equal to ya plus yb, CA, oh my goodness, let's just, there we go, CA times YA plus CB times YB. Okay, so let's call this YA, let's call this YB. This and this are two solutions to a differential equation. Cosine and sine are actually linearly independent, and that's because cosine is an even function and sine is an odd function, and they end up staying linearly independent when you multiply them both by e to the alpha t. So what does that mean? Therefore, if alpha plus I beta is a solution to the auxiliary equation, then, or alpha plus or minus I beta, then y1 of t equals e to the alpha t cosine of beta t, and y2 of t is equal to e to the alpha t sine of beta t are linearly independent solutions to the homogeneous equation. Somebody can't write. Okay, there we go. So that's nice. So what that really tells you is that you never really have to you never have to deal with complex numbers. If you end up getting a complex number as a root, then you just get two solutions, cosine and sine, times some exponential. So now let's take a look at a couple examples. So, say example 1 here. They want us to use, they basically want us to, my mistake, there we go. Solve the initial value problem. Y double prime plus 2y prime plus 2y is equal to 0, where we have y of 0 is equal to 0, and y prime of 0 is equal to 2. Now, if you go back and you look at the book, they're actually telling us to use the general solution that they cooked up in the book that involves complex numbers that they want us to use to go ahead and to deal with the complex numbers and fight them and solve the problem. But in practice, I'm never going to ask you to do that. So why don't we just go ahead and solve this problem. And so let's go ahead and do that. Let's see. So we're going to solve the initial value problem. And so this is a second order homogeneous differential equation. And what we're going to do is we're going to make the guess of y of t is equal to e to the rt, just like we did in the last section. Then that's going to give us, it's going to change this equation to being e to the rt times r squared plus 2r plus 2 is equal to 0. And again, that's going to give us r squared plus 2r plus 2 is equal to 0. And this is something we're going to have to solve with a quadratic equation. So r is equal to negative 2 plus or minus the square root of 4 minus 4 times 2 all over 2. So that gives us negative 1 plus or minus the square root of negative 4 divided by 2. And that gives us negative 1 plus or minus I. Okay, so then we get two solutions. We get y1 of t is going to be e to the negative 1 times t times cosine of t. And we're going to get y2 of t is equal to e to negative t times sine of t. Okay, so then the general solution, y of t, is going to be equal to c1 times e to negative t cosine of t, and plus c2 times e to negative t sine of t. Now we just need to figure out what c1 and c2 are. So let's go ahead and copy them, and we'll go on to the next page. Okay, so remember we had y of 0 is equal to 0 and y prime of 0 is equal to 2. So y of 0 is equal to 0 and y prime of 0 is equal to 2. And let's go ahead and use that. So first of all, y of 0 is going to give me c1 times 1 from this guy and times 1 from this guy, so that's just c1, plus c2 times 1 times 0, right? So it's just basically going to be c2 times 0, and so that's equal to c1. Well, y of 0 was actually equal to 0, so that goes in here, and so then that tells me that's our first coefficient. Okay, so then if we actually go ahead and use that, then we see that y of t then is just equal to c2 times e to the minus t times sine of t. I'm going and plugging that in because it makes the derivative a lot easier to manage. So if I take y prime of t then, I get c2 times, now we use chain rule, product rule. So we get negative e to the minus t times sine of t, and then we get minus cosine of t times e to the minus t. Oops, sorry, that should be plus. All right, now if I go ahead and take y prime at 0, then I get c2 times, it looks like, negative 0 plus 1. And so that tells me that's just c2. And then bringing this back over in here, that tells us that this is equal to 2. Because y prime of 0 is equal to 2. So we've just solved the initial value problem. We have y of t is equal to 2 times e to the minus t sine of t. And there we go. Right, not too bad. Okay, and let's go ahead and do one more example, and that should be good enough. We're going to find a general solution to y double prime plus 2y prime plus 4y is equal to 0. Okay, so that leads to the auxiliary equation. We're going to get, say, r squared plus 2r plus 4 is equal to 0. And then this r is going to be equal to negative b, so negative 2 plus or minus the square root of b squared, so it's 4 minus 4ac, so that's 16, divided by 2. So that's going to be negative 1 plus or minus the square root of, what is that, negative 12 divided by 2. And so then that is going to be negative 1 plus or minus I. Square root of 12 is square root of 4 times 3. And square root of 4 is 2, so then it's going to be just root 3 left over. Okay, so that tells us that one solution, y1 of t, is equal to e to the minus t times cosine of square root of 3t, and y2 of t is equal to e to the minus t times sine of square root of 3t. Okay, and if we want the general solution, then we get y of t is equal to c1 e to the minus t cosine of root 3 t plus c2 times e to the minus t sine the square root of 3t. And there you go. That is the general solution to this differential equation. Okay, so I think we're going to stop it there because there's really not much more to solving these equations. So just like with the last section, it's all about making the assumption that the solution is going to be equal to e to the rt, and then we get and then we just have a couple forms we plug everything into, and after that we're done. So yeah, so I'm going to end it here, and yeah, all right, take care.
Hey, welcome back. All right, so that was what happens when we have complex roots. It ends up being not too bad. You can really just use that formula at the end where we can just take a complex root that gave us, say, alpha plus I beta as a root, and then you say it's going to be e to the alpha t times sine of beta t, and also e to the alpha t cosine of beta t. And those would be going to be your two solutions. And that's more or less the entire takeaway of the section. We could have lumped it into the last section and just said all this at once, but you know, this spreads out the content a little bit and helps you get an idea of sort of this new method. So already for this upcoming exam, we have separable differential equations, linear differential equations, and we have compartmental analysis, and now we have two new sections out of chapter 4. But really, there's only one idea out of those two sections. That's finding the auxiliary equation, and then going ahead and solving and finding the roots. And yeah, so it's adding up, and I think we have maybe another lecture or two before the exam, and then that would round out everything. So that'll give you about like 5 topics or so going into the exam. Anyway, I hope you're all following and enjoying these lectures. And yeah, I'm off to record the next video. All right, bye-bye.